Hey guys, it's Aski here. I'm just putting together our materials here for a silicon drift detector experiment. I have a table of frequencies that the silicon detector that I built will beep at when atoms are present in the sample that's been x-rayed onto the plate of silicon that it reads from. So here I have a simple plate of silicon and a piece of gold with iridium and platinum and palladium. I have a piece of a key. Let's put a bottle cap on that. This XRF hooks into an audio cable interface, which goes into my computer. We look for these frequencies. Pause the video if you need to, in order to obtain the identity of these common atoms. So what I do with my silicon drift detector, what it is basically an op-amp with a transistor here and a potentiometer between the output and the input to the transformer. And the current coming in from the silicon drift detector gets sent into the transformer or into the subject amplifier terminal on the transistor, amplified by the transformer. The drainage voltage will go to the transformer and resonate at certain frequencies, and they'll co-resonate with back EMF generated on the silicon plate during the burst, resulting in frequency patterns that bleep accordingly to the identity of the X-ray fluorescent atom emission spectra under the bombardment by the laser. So this kit actually involves my laser and all the capacitor banks and the battery to it in pulsed mode or 50-watt continuous mode. You would use 50-watt continuous mode in amplifying mode, and in dampening mode you would use pulses to thicken out the rich signal. It works quite well and would be audible over a simple speaker. But the simple design right now as it stands is also just good for an audio cable. I tend to use it this way. It's connected to the silicon and it's got a subject with likely, as we've tested before, amounts of iron and zinc, amounts of copper and tin, and amounts of gold, iridium, palladium, osmium, and platinum. So when I fire the laser at this, guys, it will become incredibly energetic for a moment, and it will record onto my computer. I will amplify this recording, and we'll hear some peaks and compare it to this data. So here we go. We have a recording going. Ready, aim, fire. The shot was somewhere between right here and right here. So we're amplifying it. And we can hear it now. Let's turn on our spectrogram first to see what it looks like. After the shot was fired, about right here, you can see an increase in the activity. Zooming in, we see a lot of activity that just wasn't there before. So we'll listen to this. With noise reduction, it sounds better. That was our X-ray data. That's X-ray fluorescence from a silicon drift detector. Now, because the frequency spectrums look like they go up to about 1,000 across this whole specimen, with only a few peaks at about 3,000 hertz and 6,000 hertz being the rarest. As we can, after 3 recordings in Audacity, middle tuning, where the silicon drift device actually dampens and amplifies the wave into a resonant bypass, which sustains with harmonic values indicative of the elements present in the sample. Audio 1.2 here was recorded using the high impedance frequency selectivity mode, and it lowers the max frequency of absorbed high nuclear mass atoms and platinum group metals, which generally have high emission lines. And then there's the low impedance damping resonation circuit, which actually lowers the total frequencies and makes high frequency ion activity measurable, whereas the damp frequency makes low activity commonalities in the data resonance more provoked. So when I looked at this data, it did check with this chart, which has the actual frequency values that we're supposed to be reading in order to get the proper measurements. So what we have here were for peaks from 1,000 to some 1050 for the platinum group metals. The middle shift here was relatively effective at predicting exactly what frequencies they'd show up at. These are just simple approximation curvature contours that we transform to obtain the best fit line of frequencies. But for the upshift, we had very accurate measurements for platinum and gold. The copper and zinc stayed mostly the same anyways, and they were consistent. The iron was also very consistent. In fact, most consistent for the tuning shifts that I'm describing. But in the damp downshift, we had gold showing up at no more than 1800, and that was also a very obvious thing. On the silicon drift detector, damped is this way, middle is right here, and fully amplifying is right here to the right, or the counterclockwise. So it looks like we're getting XRF results from our gold bar, our little key, and our steel, and it's at least 90% overall effective in obtaining the atomic composition and what approximate rates are in there. You can check by buzzing and checking relative pitches all day using the chart, or you can use a method with computerization and approximation. But this silicon drift detector I developed, which again, it's simply a transformer which two leads go in and out of a resonation between a potentiometer and an amplifying transistor. The transformer takes in current from the input signal, amplifies the transistor signal, which is fed by the input signal as well. And then after the transistor output, it may either recycle back into the transistor amplifier via the potentiometer, or it may be resonated back into the unit. The output is the refined output from the potentiometer after transistor amplification. An audio output was assigned, and a little electrode to contact the silicon was assigned. If you build one of these, they chirp and they give you frequencies for your XRF signals. They're beautiful. I recommend this circuit over a standard XRF. They seem very, very accurate and good at picking up oxygen. That's basically all I have to say, but this was just another installment in my electron sling laser project videos and instructional guides. I may make a video on how to make one for yourself, but the key is you have a counter coil that's in a knot, not a wrapped coil, and the knots turn along a direction from the back, whatever behind magnetic fields on the spark gap, to over and past the spark gap where you place the tuner coil. The rest of the circuit is in the schematic. Nothing else should be very complicated about establishing the housing for a laser like this if you need to. They perform amazing things. They have a fractal wave source. The output is 15 kilojoules, 15 to 30 gigawatts of max pressurized power during fractal obfuscation, and it's capable of fusing 3 milligrams of gold per single 15 kilojoule hit, which contains 3 kilojoules of visible light. Using my special solution anyways. I'll keep that a secret and I'll let you guys play with these, but these are fusion ready lasers with a very fast release and a very decent power storage. They are useful for so many things. I just wanted to show you XRF, one of the most important analysis techniques for being that sure that your water is pure. So there you go, another survival guide video about my laser with science and applications in science. I hope you guys have a great day. Enjoy.